Yeah, thank you for the introduction and thank you for having me here. I'm very glad to be here today in Rennes. I never was in Rennes before, and despite a slight problem with the metro this morning, everything worked fine. So yeah, the talk is about obfuscation and concealment of network traffic of flows. Not that I make much of a difference between the two terms, but this is also like a summary of one of the research domains I'm working on since several years. And yeah, let's see. So I'm from Worms. That's not so far behind the French border. And actually I live around here. So I drove like this way here over Paris and then there. And Worms is one of the oldest towns in the country, and yeah, roughly 85,000 citizens. So I just placed my laptop screen a little bit differently so that it's easier to look at for me to look at the screen from the side. I want to start with a quote from Donald Knuth, and he wrote, that's 22 years meanwhile ago, that in his own field it was once possible to know basically everything there was to know about computer science. So that was when he was a PhD student, I think. And so today means 2001, it's way too big and nobody can cope all of it. And that's a little bit problematic in terms of keeping an overview. And I come back to this quote later. For now, let's start with the term information hiding. So information hiding essentially means that we hide something in something else. Like these images are just taken from Wikipedia. They are the classic examples. So the image of the cat is hidden in the tree image, or watermarking is another example of information hiding. And but that discipline is quite old, so it dates back to ancient Greece, where they used human skin and tattooed messages on it, and later astragali and so on. And what is, I think, pretty known are newspaper messages, secret messages in newspaper announcements and so on. And obviously this technology was, like cryptography, was enhanced during war times. Now, information hiding became digital in the 20th century. And here we have like hiding information in file systems, in all types of digital media files, in network traffic, and most recently in IoT and CPS devices, and also an emergence of methods that hide data somehow in machine learning models. My focus on today's talk are network protocols and network services. So this is just to give you an impression of how this can be placed in the history of that domain, which is similarly like cryptography pretty old. In comparison to the ancient methods, they are now much quicker. So sending a network packet obviously takes less time than tattooing the message of the head of some servant or so, sent that person to the destination, maybe travels a few days or weeks and then comes back. So the reply is also much quicker. And that allows for services like transferring secret data for malicious communications, data exfiltration, things like that. And in that domain, there are quite a few related terms or also outside. So one is, I would say, censorship circumvention, and they use terms like traffic morphing and traffic obfuscation. When I chose the title of the topic, I just picked randomly, more or less, a few of these terms. I made them broad, but they largely overlap. And obfuscation of traffic means we change the characteristics of the traffic to let it appear as something else. For instance, we can let Tor traffic appear like Skype traffic or something. Then there's traffic flow watermarking with flow linking. This is a bit outside of today's talk, and this discipline of network information hiding with network steganography, covert channels, traffic concealment techniques. Sometimes also tunneling is used the wrong way as a term. And here the idea is to hide the fact that the communication is taking place. So we don't want, if we encrypt the information, then obviously it's visible that there is some random data, there is something. But here the goal is to prevent that someone recognizes at all that there is something. And more or less a subdiscipline is the network side channel topic. So the focus of today's talk will be rather broad in the sense that I will cover these disciplines in a broad manner, and then I will go a little bit into the details of the traffic concealment domain. So where does this all belong to, and why don't we just use Tor? In fact, Tor is obviously used. Tor is used to circumvent internet censorship and to get our information somehow from A to B. Now, there are tools like StegTorus. I think that was published in CCS last year. No, 11 years before. And that provides some Tor proxy to additionally circumvent filter technology, because Tor traffic has some characteristics that you can use to filter the traffic. And this is what also regimes around the world do, to filter Tor and to block it. And they, with traffic morphing and network steganography and traffic obfuscation and traffic circumvention, it all means more or less the same. Several methods arose that let certain characteristics of the traffic appear like other traffic. For instance, you can adjust packet sizes or packet timing. So you take Tor traffic, you adjust the packet sizes to match the timing of Skype traffic. You adjust the interpacket gaps to match Skype traffic if you want it to appear like Skype traffic. Maybe you want to have it appear as some completely different traffic. That's also fine. You just have to adjust the characteristics. And this is done since many years. You also see 2012 SMP. So this is not new. Actually, such things are way older. But the essential idea is always the basic mimicry system. So we have some recipient that tries to distinguish between the model and the mimic. So like in biology, you have a prey-predator model. And in many cases, some type of animal wants to mimic, let's say, a leaf or some other animal that is dangerous or something. And the recipient tries to distinguish that plus here. It tries to identify what I can eat and what I shouldn't attack. Okay, and the problem that I focus on since many years now is the one of scientific reinventions in such a domain. A reinvention is if when someone discovers an idea that was already there, but publishes it again under different terms because the person often just doesn't know that the idea was already described, but in other terms, in another sub-community or something. And that leads to scientific reinventions and also to redundancies in research output. This is a problem because of many reasons. I don't want to go into the details here. One reason is also funding and efficiency of science. But obviously, if you have an idea, you want your original idea to be cited, and you don't want to be the person who is the second to publish an idea only to find out 10 years later the idea got already published. And so in 2013, and this is kind of the first part of this talk, we started to analyze the commonalities of concealment methods, hiding methods that there are existing, mainly in steganography and covert channel research, and we widened this focus in the last couple of years. So we surveyed hundreds and hundreds of techniques to identify the commonalities and to unify their terminology, their description, so that if I pick one, then I can see, okay, this is also known under some alias terms, and I can look them up as well, and I see the links between the subdisciplines so that I can make like a connection, and everybody who uses this taxonomy can make these connections too, and it's easier to identify what is already there in terms of research. Obviously, this can be done for essentially every subdomain of cybersecurity or any scientific domain. And this was more or less inspired by biology, but I come back to that later. So in the information hiding domains, we have the classical tunneling, stego, network covert channels, obfuscation of traffic, and so on. And if we analyze their goals, then we see they are largely overlapping, and also they are not so much different, especially when it comes to the methodology. So, for instance, stego and network covert channels, they want to hide traffic, but what do? I take the simple examples. They modulate packet sizes, inter-packet delays, they influence the acknowledging behavior of traffic, and so on. If you do traffic obfuscation, censorship, circumvention, traffic morphing, and look into that literature, and well, they want to change some characteristics to let the traffic appear as legitimate. What do they do? Well, they adjust packet sizes, they adjust inter-packet delays, they adjust acknowledgement sequences, and so on. And as you can see, there are fundamental overlaps in terms of what they do. If we look at traffic flow watermarking, they have a different goal as well. They want to embed information, for instance, about the origin of some traffic in the traffic to link flows in different attack scenarios. And they do padding, which is packet size adjustment. They modify inter-packet delays, and so on. So it's roughly, again, the same. And the point is, why not unifying this? Why does every sub-community has its own venues, own research terminology, and ignores each other? So that's one of the key points of today's talk. Good. So we can take Knut's quote again. It's the same like before. We travel a bit in time, and now 20 years later, we replace that with network concealment research. And there was, when I started as a PhD student, it was not so much stuff going on, but I was finished when most of the papers in that area that appeared in the last like 10 years in the fields grow, so that was not published back then, but we have a huge increase in the number of publications, and topics became bigger and built sub-communities and so on. And now it's time to bring things back together. But the problem is that there are like hundreds of techniques and terms. And it's difficult to keep an overview and to prevent these reinventions. And for this reason, the idea was to develop at least a common taxonomy in the first step. But the problem is that it's a massive process, because if you do not involve the necessary, or the people of that are coming from the particular communities, they more or less likely either won't accept the terminology or they are just not aware of it. I mean, you can publish it, but in the end you publish in some community's journal or venue, and then the other communities will ignore this result again. So it doesn't matter, and in the end, and the goal would not be reached and the goal is to reach as many people as possible and all the communities. So this started 2013, now 10 years ago. with Sebastian Zander, Bernhard Fechner, and Christian Herdin, and for covert channels and steganography. And result was a first survey paper in which we said, okay, there are patterns that are common. And in that paper, we analyzed more than 100 hiding techniques published since the 80s in that domain. More or less everything that was there in covert channel research, but ignoring like all the censorship circumvention, all the flow watermarking topics, and so on. And then there were lots of intermediate publications. Some added new patterns, others revised the taxonomy. Colleagues from Magdeburg applied the taxonomy then to industrial control systems, and it worked as well. So they extended things quite nicely, and then the consortium grew. We are now 12 people from 7 institutions, and we had a revised taxonomy in 21, and last year one for just side channels and indirect channels at Asia CCS, and well, since last year we have the more or less final revision of the taxonomy for steganography under review. It's still in revision 0, so it's close to getting 1 year in which we wait for the reviews, but this is online as a preprint. And there's lots of other stuff in the pipeline. So this has some history, but all till here is, so except the orange one, is still exclusively focusing on covert channels and steganography, and misses still the whole censorship circumvention part and so on. And there's still a lot to do, and maybe this can be transferred to other domains like code obfuscation or something as well. I don't know. Could be debated. I cannot tell. So the original taxonomy, just to give you a brief overview. I don't want to go into all the details. It's also not important at this point, but the idea was to have some major categories. Either it's a covert storage or timing channel, that's some traditional distinction. And then you have some modification of payload or non-payload. And if you modify non-payload, like protocol headers, you can keep the structure, you preserve the structure, or you modify the structure. And all the gray ones are patterns, and they can also have sub-patterns. So it turned out that in this first version, 109 hiding techniques were actually describable by only 11 patterns. So there are 11 really novel ideas present in the research community, but described through 109 techniques. But the core idea, the pattern is always the same, or more or less always the same. And I don't have a plot here for the distribution of the patterns, but some patterns are rare, and some patterns you have like 20-something examples in the literature. And all say, okay, we do something new here. We do that and that for that and that protocol, but somebody else already did it for a slightly different protocol, and it's just exactly the same, with more or less the same results. And that was one of the interesting insights. This taxonomy grew over the years, so there were a few new ideas, because then we were looking for what else can be done to extend this taxonomy. And several people contributed patterns to this taxonomy, because they said, well, we can do something really different. And that's what you can use such a taxonomy for, because you just need a few moments to check what is there, and then you can think about what is really new, and to prevent reinventing the wheel once more. How does such a pattern look like? Here's a simple example. The element positioning or interpacket time pattern. So this is the one in brackets is the network specific name, but actually it's positioning of an element. So we position the network packet in time. And what we can do here is, for instance, we can send bursts of traffic, or we modulate the gaps between network packets over time. And this pattern has been described like 40 times or something in the literature under different names, but this is how it looks like, the core element of it. It's a little bit more complex than that, but that's not so important at this point. Okay, now how did we develop this taxonomy, and how did we aim for making sure that it's actually used? Because, I mean, many taxonomies are published, people read them, forget them, and that's it. That IEEE preprint server, I forgot the name. It's not archive.org, but another one. So let's start with the problems. And this is all based on that paper. And as mentioned earlier, the work was inspired by biology. This guy here, Carl Linnaeus, who is the main inventor of the taxonomy in biology. But back then, in the 18th century, I think, there were other taxonomies in biology. Now, why did this taxonomy survive till today? Any idea? What is the great thing of this taxonomy? You might not know it, but you might have heard terms like, oh, yes.
It still applies?
Yeah, it still applies, right? That's a very good point. It's generic enough so that it's you can still describe everything, and also what is in the past. Like animals that are not existent anymore, you can still describe. What else can be, well, could potentially be a characteristic of this taxonomy? Any idea? It's easy. It's easy to use, and I start with some problems here to illustrate how we got inspired here. So, for instance, we take that packet size covert channel. Has lots of names: size-based covert channel, packet length, packet size, covert channel, field length, padding size, and also you can replace, of course, covert channel with traffic morphing and so on. You end up with quite many combinations. And the solution is to provide an alias. So we have one name and we provide aliases for all these things. Okay, so that's an easy one. Next one is, who cares about another taxonomy? As mentioned, they are published on a regular basis. People forget them. And so the idea is to involve the community, to let people contribute patterns, to say, hey, you can have if you have the amazing new idea, you are maybe the creator of the next pattern, and then the community will associate you with that. Also, we cite work. If someone tells us, hey, I have published something that belongs to that pattern X, then we say, okay, that's good. Send us a link. We link your paper as a reference, so your work gets linked on the website and so on. And yeah, so it's a very open thing. It's not that only some people tell the world this is the taxonomy. No, it should be a community thing. Otherwise, nobody might want to contribute to it. Then the next thing was, I said the terminology in biology is an easy one in the sense of it's applicable. And that's because it has a binomial nomenclature. So you have two terms, two words to describe something, like Canis lupus as the gray wolf. Now, if you want to be more specific, you can add words like dingo for the Australian dingo. And so you can be more specific by adding more words, but in the core idea is you have just two, and it's easy. So everybody can apply this. And we did the same in steganography and circumvention research and so on. So let's say we have a state or value, and we modulate that state or value. Fine. It could be that we want to be more specific. Maybe it's a least significant bit or bits. Or maybe we want to be more specific and want to say, okay, it's in a network context or something. So we just add words. And that's pretty easy. And just a transfer of this guy's idea. Then the next problem was the previous taxonomies were always specific, like for image steganography or for network steganography. So they did not need to consider that a term might have a different understanding in a different domain. But it's the case if you want to unify it. Just to give you one example, if you transfer an image over the network and that image or an audio stream carries secret information, from the network perspective, that's payload with secret messages in it. Not go into the details of this because it was not working. We thought this will work, but it didn't. So here's the easy way. We have elements that contain sub-elements as many times as we want. And these elements have a state or value, and that's it. So we describe everything in a very simple object-oriented approach. And elements, for instance, in a network can be network packet, a header field, the time of occurrence of a packet, the number of packets in a flow. In digital media, it can be a pixel, it can be a PNG file header. In the CPS can be a sensor value, sensor value not, but a sensor, an actuator, and so on. In file systems, it can be an inode, but it can also be a parameter of an inode. And values are the actual values, like packet size value, or the temperature value of a sensor in a cyber-physical system. Here's if we have a flow and like this contains several packets, they are all objects, elements, and they contain sub-elements like more packets, and each packet can contain elements like this IP version 4 header, version, options, destination, and so on. And this can again contain sub-elements like the options, and they contain sub-elements and so on. And all of this can also have virtual elements like number of packets in a flow, duration of a flow, time of occurrence of a packet, and so on. So this is applicable also to file systems and whatnot. Another problem is that patterns are often hybrid. And hybrid patterns, that means that we do two things. Like in this paper here, we triggered reconnections of clients in a Wi-Fi network, and a receiver monitors the reconnects in the Wi-Fi network, which encode the secret message. And so first you send some certain header, you modulate some values, but the receiver interprets the positioning of events over time, which are the reconnects. So sometimes you need multiple patterns to describe something, but that's possible and no problem. Sometimes the embedding and extraction process differ. That's also possible to describe. And because we have embedding and representation patterns. And we ended up with this simple main taxon. So either we modulate the value or state, or we change the element's occurrence. for instance, the number of elements or the position of an element, like a pixel or a frame in a video. And yeah, so that this is extremely simplified, but it's like a first layer. And everything fits into these few patterns. And the representation patterns are simply derived from these embedding patterns that are shown here. I just want to give you now a few examples to underpin that it works. Okay, so the idea is I go through different domains, and I start with network stego, and I go through side channels and so on. Just one example per domain to tell you how this fits. So one would be network stego. I pick one pattern, that's the artificial retransmissions one, where you artificially craft TCP retransmissions to signal hidden messages. And that would be network element enumeration, because we duplicate packets. Check. So that's the first. CPS steganography. Encoding a secret signal by influencing the response time of an actuator. So you request some data and you get some or some action, and you wait till the action is done. So you do element positioning, because you position that action in time. Works also. File system, placing secret data bytes in unused file system blocks. That would be file system reserved unused state value modulation. So we added to state value modulation the reserved unused category because we have some unused bytes, and it's file system specific. So we can categorize all methods that do that in that pattern. Also easy. Text stego is probably the easiest. Modifying the features of characters in text, underlining and such things. I'm surprised to see papers about this still today, but we actually included it only for completion, then did the survey, and there's still work done on this. And it turns out also malware uses this because it's easy to hide, for instance, in source code, in HTML and so on. It's quite, we have lots of space and little effort. So text, characters, state value modulation. Also easy to categorize here. What do we have here? Inserting a blue screen or blue pixel at some location. That's digital media element positioning. Okay. Side channels. I picked an interesting one from Sebastian Schinzel. And he had one side channel in, I think, 2011, where he sent lots of requests for a username to a website and measured the response time. And the idea was you sent like 1,000 requests for Adam, 1,000 requests for Eve, and so on, and you measure the average response time as exactly as possible. To differentiate between services that usernames that exist and that do not exist. Because if the username exists, what is the step that is taken next? The password will be checked. So that consumes additional time. So the response time will be higher. Only a tiny fraction, but this is nothing else but network element positioning again. It's like an interpacket gap that we measure. Traffic obfuscation. Size padding is trivial. Network element enumeration, because we enumerate the number of bytes at the end of the packet. If we add more bytes, we add more. If we add fewer, then we add fewer. Okay, but this is a little bit superficial. So where do the details go? Well, I don't go too much into this, but we have domain-specific taxonomies. So we first say, okay, the generic pattern is so and so. And then come domain-specific taxonomies, still partially in progress. And then we have a unified description method that allows to describe all the details of the research method. of the hiding method. And this is aided for scientific replicability, so that experiments can be easier redone. And we added this method because we did another survey and we checked how many papers of 100 and I think 130 something describe which attribute. Like an application scenario was described in well, a little bit more than 100% of the papers, at least partially, but robustness, channel capacity, countermeasures, even countermeasures were less than 80. So with a unified description method that tells you, okay, first you describe this, then you describe this, then you describe this, that eases the understanding, the scanning of papers, and the comparison. Yeah, details of the description method I skip at this point. We have design rules. We made sure also that the previous taxonomy editions fit into the new one, so it's backwards compatible to everything there was. And we did this also for indirect channels and side channels. And we categorized another, I don't know how many, quite so more or less everything that was there, and found 3 patterns. This is mostly work by Tobias Schmidbauer, one of my PhD students. He's about to defend his thesis next month. And so the 3 patterns here are the redirector, proxy, and dead drop. So either you have some sender that makes some system redirect data somehow to a receiver, or in the proxy case, the sender influences the proxy, which is then measured by the receiver. For instance, by if you send, a simple example is to send many requests to one system so that it's under more load, so that the response time for a request of the receiver takes longer. That's the classical timing side channel. Or dead drop. And this is something new. That's a type of network side channel that exploits essentially protocol caches. For instance, the ARP or the NTP cache. So you send data and you make sure that some system caches the data in the ARP or NTP cache or something. And some other system can extract the information for a limited amount of time. So that was also something interesting. And yeah, everything, and this taxonomy is built on top of the other again. So it's also backwards compatible. All right, so that's the first part of the talk. Now I want to speak about something pretty different, namely what can be done with that taxonomy and some nice new examples of recent ideas. And to that, I just asked the question, okay, what can be done with the taxonomy? Well, multiple things, like identifying gaps and so on. But here are a few examples. And I want to start with the simple pattern that we already know, the inter-packet times or element positioning one. So packet inter-arrival times are modulated. Okay. Now, what can we do with this? We can try to detect it. And I just show briefly 2 very classical detection heuristics with like almost 1,000 citations. So this is very, very, very standard. This is epsilon similarity. So you record the inter-arrival times, sort them in ascending order, measure the relative differences, and put a threshold in it to distinguish between covert and non-covert data. And the other one is the compressibility score. You record the inter-arrival times, encode them into a string of rounded inter-arrival time values. You select the compressor and compress that, and the resulting kappa value indicates how compressible the information is. And if you have an artificial signaling, then you have the same few symbols occurring over and over again, like 0.2 and 0.5 seconds or something for secret 0 or 1 bit. So compressibility is high. So in the end, it's an entropy measure. Okay, and so these are standard and very, very much cited. And we played around with this and did something we call countermeasure variation. So we take one of these methods, like get some input, like under arrival times, we calculate compressibility score, get some results. What we do is we just replace this with, for instance, packet sizes, adjust the measure, and get hopefully useful results. That's the classical approach. And we did this for almost everything there is in the last years, like message ordering, like network packet ordering, and so on. I skipped the details here, but it works pretty fine. So we get really good results in the end for detectability. We also replicated several experiments here with a test bed we call Worms Distributed Covert Channel Detection Framework. And we replicated these classical experiments. And the interesting thing is, maybe due to a lack of space, but the original papers never explain you everything and all the problems such methods have. And we played around, we did what was described in the literature, but we extended the parameters. So we replaced compressing algorithms with others. We used different network flows. And it turns out this compressibility score, the green one is legitimate traffic, and the red and blue one is covert traffic, different types of. And as you can see, depending, for instance, of the rounding precision, this changes a lot in terms of how much the data overlaps. And we also played around with different media, Ethernet and remote networks. And as you can see, the compressibility values differ a lot. So even in the original CCS paper, they say, okay, the typical values are this and that. But this is not so easy. It's not really true, because the values they had were in this range. So they had remote connections. But in a local network, it was totally different. Also, compressor makes a little bit difference, and some other factors as well. And my point is that research literature should include, if possible, such circumstances. Like if we even take Ethernet, we actually need to differentiate between the types, because the interpacket gaps differ quite a lot. Okay, now one of the last cool things, one of the two things I have still in my slides is epsilon Kappa-Libur. So we took the epsilon similarity and the compressibility score, because they were more or less the highest citing detection heuristics in covert channel research that there are. And normally, this is a bit simplified, but normal legitimate traffic, if you sort the interarrival times of a flow, it looks a little bit like this. Covert channel, in the most simple case, looks a little bit like this, because you have a 0 and a 1 symbol. There are several ways to optimize the channel, but what we did is essentially the green one. We have some slight slope and some steps here that is enough to break both detection methods at the same time. So the epsilon similarity score usually for most covert channels has really good detection results. So we have an AUC of 1. Of course, we used lots of different parameters here. This is just a summary over all configurations that we used. And with epsilon Kappa-Libur, the AUC goes down to almost 0.5. And also, depending on the interpacket gaps, which is this tau value here, it doesn't change too much to the good, and for the compressibility score as well. I mean, the average AUC goes pretty much down. So we were quite happy and submitted this to TDSC, and they said, well, what's with the most recent algorithms? And we checked, first of all, GAS, which is the more or less actually the latest and the best covert channel detection system, at least that I know. And GAS uses different features from traffic flows to feed an LSTM and then discriminate between covert and non-covert, but not for the simple ones, but except for all the sophisticated types of network covert channels. So not the one with two symbols. And it turns out that so the original covert channel traffic recordings are the orange ones, and they detected everything with almost 1.0 area under curve. And we used their code that's on GitHub to implement our epsilon Kapalibor there. And epsilon Kapalibor cannot be well detected by them. So the AUC is between 0.05 and 0.6 for the LabNet. And for the bigger network, a remote connection, it can still go down to 0.7 about, but can partially be detected as well. So we can decrease the performance of this very best method. It was still impressed back then quite well. And we picked the second one, Snapcatch. And Snapcatch uses image processing methodology to train, I think, a support vector machine, if I'm not mistaken. So features like average gray value and things like that. And it was the only one we found that could detect epsilon Kapalibor as almost as good as all other covert channels. But because several features depend on the pixel values, what we did was, if I just draw this here, maybe, so usually, I mean, let's say you have an inter-arrival time of so-and-so, and the average pixel values between, well, the pixel has always a value between 0 and 255, obviously. So you map legitimate traffic, and maybe it has some values around here, usually, or whatever, and the covert channel might be in the whole range. So what we did was we added one outlier so that the rest of the covert channel's data is shifted to pixel values that overlap the legitimate. I don't remember whether they were like the first half or what. And that resulted in a easily decreased detection result as well. So I think it's 0.6. This is mostly work by Sebastian Sillian, one of my PhD students as well. And in this case, we just tricked the extraction of features. Okay, what else can be done? Last piece for today are history channels. So everything in the literature so far, I mean, covert channels exist since 1973, looks at what is there. So data that we currently transmit, so we want to send the secret information, so we keep it, if we take it, we send it somewhere else, and it's extracted. But what if we just point to the history, like traffic we have seen in the past, just recently? And this paper is still under review, but the preprint is online. Unfortunately, it got rejected after rebuttal last year at the CCS. We monitor the network traffic and we say, okay, this packet that we just saw, that somehow contains a hash or something that matches our secret message. And the idea is to send only very few pointers to traffic that matches. So if we have observed several packets over time, we compute somehow hash function over the content of the packet, check whether the hash matches. And at a certain point in time, we find a packet that matches the hash. Then we send a legitimate ARP request that the system always sends just to, let's say, resolve the MAC address of the router in the network or something. And the only covert information actually is that this packet says, okay, the previously seen packet contains the secret message. So this changes the fraction of secret bits that you need to transfer not the fraction, the proportion of signaling to data packets. Because we do not need to send this packet that contains the secret information anymore on our own. So we cannot cause an anomaly. And there are at least 3 follow-up papers on this right now because the performance is not so good. I cannot speak about the follow-up papers because they are not submitted or published anything yet, but this idea gives us the opportunity to enhance, for instance, sensor chip circumvention in the future, because if we know that some systems are on the same path, then they could just send a signaling packet and tell the recipient, okay, the previously seen packet contains the secret message. It must be a fixed position and so on. And there's an optimization problem that is also described in the paper. And you have robustness issues also described in the paper. And the performance is currently low, but it works. And you can also even have a prediction channel that says, okay, the next packet is most likely one of interest, because in more or less deterministic systems, you can anticipate that, for instance, a new sensor value is pushed, or that some ARP request is sent again because after some typical amount of time it's sent, something like this. But this prediction-based channel is still in progress. We currently analyze how well this can perform in the end. And in the end, this is of course element positioning or inter-packet times pattern again that we exploit here. It's just a gap between the packets. Okay, so what's the key takeaway messages here? So first of all, large fraction of information hiding related research, which is all the blue stuff here in brackets, overlaps. And I think personally, it's my opinion, we should find common terms also to prevent reinventions, just doing everything again and again, building sub communities and ignoring other communities. We need to come together and find common basis. And this taxonomy might be a part of the solution, and allows to categorize methods of all these different domains. We have several problems solved, like applicability, provision of detail, hybrid methods, design rules are there. We are capable of handling new variants. So for instance, this epsilon Capalibur can be categorized. And also DIST, which is the history channel. DIT is just, did you see that? That's the title of that paper. And it's a multi-level approach. So we have the generic taxonomy, a specific taxonomy, and then the unified description method. What are the next steps? So we finished more or less the generic taxonomy, and we have the indirect hiding patterns last year. This is done. Then we want to fully integrate censorship, circumvention, side channels, traffic flow, watermarking. This is a good fraction is done. There's just a follow-up paper that shows that the patterns that I've shown you can be used there as well. But there are a few subdomains like digital media steganography, watermarking, digital watermarking, machine learning-based stego, code obfuscation that is partially not done at all, and in some cases a little bit done. We need to check whether it really works with the same taxonomy or whether we need to adjust something. And this should result in some years. I wrote here 2025 and further in a generic taxonomy for all of this that will hopefully exist by then, and hopefully it will work. I don't know whether it will work. I just hope for it, because then everybody speaks the same language. And then I would have reached my personal goal in that sense, because my frustration started when I was a PhD student and saw, hey, these guys do something puzzling me a lot. Now I invested lots of time in preventing this for the future. So yeah, if you're interested, join us. And of course, not just I did invest the time, the whole group. Under patterns.ztt, ZTT is the institute that I'm the scientific director of. We are like 30 people, and we are the more or less the research facility of that university. And my papers are on my website. This QR code just paper, or maybe to the website, I forgot. And I think that's it. So thank you for your attention. And if you have any questions, just, yeah, I'm here to answer them.